Okay. So for the MOSFET lectures, I am following part of it from Sedra Smith Microelectronic Circuits. It is, I think, a very older version from where I made the notes, but it doesn't really matter at this point. The concept hasn't changed over the last 10 years at least on whatever we are going to read up. Okay. I'm showing you here perspective. Now this we are discussing about MOSFETs. MOSFET is metal oxide semiconductor field effect transistor. Metal, basically the gate used to be a metal before, so it's shown over here as a metal. Okay. So okay, so here it is shown as this is the metal, which is the gate. Gate used to be a metal in the olden days. Okay, in last 30 years, it changed into polysilicon. The gate was made of polysilicon, which was no more a metal, but still the name MOSFET continued. And in the last, I think, I would say 10 years or so at least, it has changed again back to metals. Okay, so the 28 nanometer devices, okay, do have metal gates. Oxide is the interface here between the gate and the substrate. Okay, and then semiconductor, the substrate is semiconductor. It is a p-type substrate, and it has 2n plus in case of an NMOS. In case of a PMOS, a p-type, so this is going to be an n-type substrate followed by p plus and p plus over here. Okay, and I'm sure you're familiar with this. What is the notation of plus? Plus means more doping. Okay, more concentration of dopants in there so that the majority carriers are good enough. Okay, and P substrate is denoted as just P type. P plus means a concentration in at least an order of magnitude more. Okay, so metal oxide semiconductor. Now field effect transistor. Keep in mind a transistor it's a means it does a transfer function and it converts a voltage into a current. Okay, so the transistor is a voltage to current converter. Now the field effect, the way it does that conversion from voltage to current is due to electric field. Okay, in case of MOSFET, there are two fields. One is, we call this as the vertical field, and then the other is called the lateral field. These two fields which cause the effect of for the MOSFET for the characteristic of the MOSFET. Okay, so there is a vertical electric field which sets up the condition. Okay, and then the lateral or the horizontal, if you want to, whichever way you want to look at it, it leads to the flow of current between the drain and the source. So the field effect. So that's a reason why it is labeled as MOSFET. Okay. Now next thing that I wanted to ask you, and this is the cross-sectional view. Okay, that this is a three-dimensional perspective view. So now if you see, this becomes the width of the transistor. This is the width of the transistor, and the length of the transistor is given over here. So this is the length of the transistor. Okay, so this is the perspective view. The length is the distance between the source and drain. So there are two kinds of length. One is called the drawn length. Okay, so let's call it as a drawn length. And then the second is called the electrical length. Okay. Now, a drawn length is what is actually physically getting fabricated, and the electrical length is what finally the length of the channel due to the drain source voltage or something. Okay. Any questions?
Sir, could you elaborate on electrical length?
Oh, electrical length is drawn length is a physical whatever you are doing the fabrication. Actually it is a physical distance between the source and the drain. Okay. Now, the electrical length is when I apply a certain drain voltage, then the actual length, we'll get into the details what defines the length actually, where the carriers are. The length, actual length keeps on reducing, and that is due to a phenomenon called channel length modulation. So that is what the electrical length. So electrical length is different from the drawn length. Electrical length is due to the electrical parameters, that is the source and drain voltages. Okay, so now this is the cross-sectional view. Okay, so this is a 4-terminal device. Gate is one terminal, source second terminal, drain is the third terminal, and the body is the fourth terminal of the transistor. Okay, so you already know all these things. I'm just repeating. So again, there are two types of MOSFET. One is the enhancement type. Okay, and the third is the depletion type. Now let's try to understand why is the name enhancement given. Enhancement means you are going to enhance something. So what happens is the voltage applied enhances the quality of the transistor and makes it conduct the current. That's why we call it enhancement type. Depletion type, even in 0 voltage, it is going to conduct current between the source and drain. That's why it's called the depletion type. Okay. Now another name of MOSFET is insulated gate FET, but it is a slightly different from MOSFET. IG FET is a little bit different, but not exactly that, because but the construction is different. So let me. Okay, was there any feed through or something? Are you guys able to hear clearly?
Yes, sir.
Yes, sir.
Okay. Now, as I said, enhancement type MOSFET, we are going to analyze that, and we are not going to discuss much about depletion type MOSFETs, because in an integrated circuit, and for that matter also in PCB level, board level, most of the MOSFETs that we use are enhancement type MOSFETs. And depletion types are used, but very rarely. I mean, there are very special applications where you might need depletion type. Now, enhancement type MOSFETs, there is an N channel MOSFET and a P channel MOSFET. So, what is shown here this is an N channel MOSFET. So, N channel MOSFET is on a P substrate. So, N channel, because these are the source and drain are N type, and the channel which carries the current, with the channel that is formed here, is made of electrons. Okay, and in case of a P type, this will become P plus. Okay, and this will become P plus, and this will become N. And usually what happens is that there is, when you buy a silicon substrate, you have one substrate which is typically P type. Now on that same thing, you have to fabricate a PMOS as well. So what you do is, so let's extend the substrate a little more over this side, this way. Let's say this is continuing, the substrate is continuing. Now I want to fabricate a PMOS over here. So what happens is that for a PMOS, the body has to be N type. So, but the substrate is P type. So what we do is we make something called an N well. Okay, we call that an N well. So that becomes the substrate for the PMOS. And then we make the source P plus over here, and the drain P plus over here. And as usual, there is a gate. This is the oxide, and this is finally the gate where you make the contact. This is the source, and this is the drain. So now, one more thing that you might be noticing here is that this oxide actually overlaps the substrate a little bit. Is the red pen visible for all of you?
Yes, sir.
Yes, sir.
Yes, sir.
So you can see that this is overlapping a little bit. So I don't know if you have studied the device process fabrication. This overlap is unintended, but it happens due to the manufacturing processing technique. Okay, so it is not intentional. We do not actually want it, but it happens because the way the ions are diffused, the N plus diffusion is done. So it happens, and this is called an overlap. So there is a gate source overlap, gate source overlap, which is not desired, and similarly there is a drain source overlap. Okay, so it is not desired. Okay, but it happens because of the nature of the way the device is fabricated. Okay.
Sir,
Now let's now another thing that I wanted to point out also is,
sir,
yes, go ahead, please.
sir, it's drain source or drain gate overlap.
Oh, sorry. Good. Drain gate. My bad. My bad. Thank you. So wait a second. Um, this will be drain gate. Drain gate overlap. Gate drain overlap. Okay. Thank you for pointing that out. So please, all of you, if I sometimes when you're talking, you might miss out something. So please correct me. Okay. And if you have any questions, please do not hesitate to do so. Do the necessary corrections. Okay. So now another thing that I wanted to say here is this is the source. Okay. What is the meaning of source and what is the meaning of drain? And why is it called a gate? Why did they name it as a gate? Why did they name it as a source? And why did they name it as a drain? You have taken introduction to electronics. Anyone?
So it supplies the carriers and drain through drain they go out.
Good point. And why is it a gate?
It controls the flow.
Yes, just like a gate of your house controls the entry and exit of people, the gate controls the entry and exit of the carrier, and the carrier's source provides the carriers, and the drain drains out the carriers. Okay, so you will see that in electrical engineering, most of the names that you come across, they will really have some physical meaning. Okay, so without that, why is something called a depletion region? What is the meaning of depletion region? Deplete means what?
No active carriers present.
No active. Depletion means what? A
Less.
region that
Less
Reduction.
doesn't
amount
have
of
any depleted of carriers.
Sir, reduction.
Lack
It is
of
depleted of carriers, right?
lack of carriers.
Yes.
Lack of mobile carriers, yes.
Mobile carriers, yes. I mean, see, carriers are, I mean, one that is depleted of carriers, does it have any charge? Does it have any
So
charge?
yes. So yes.
It has the ions
yes,
in it,
yes.
right? Okay. So anyway, so now let's get on to the next thing. Okay, so we will do this analysis is we'll do a qualitative analysis first, and then we'll go into a quantitative analysis. Okay, I want you to remember the pictures as we go along. So what I'll do is after this lecture, whatever notes I'm making on this, I will also upload with the notes if there is something significantly different. Okay, otherwise any of the videos will be there. You can download the videos. And that will have those annotations. Okay. Now, in order to do a qualitative analysis, we start off with the source and the drain connected to both ground. Okay. Now, keep in mind here you can see that we have I have this dotted over here, and this dot denotes the depletion region, right? So now let me test your basics. Why is the depletion width smaller here, and why is it larger here?
Sir, depletion region is smaller for a high concentrated region.
Okay. I hope that is clear to you. Good point. Good. So the depletion region is smaller because the concentration is more. So a lesser area is required to uncover a certain amount of charges here. Now, if the concentration is less, you need more number of much more area to uncover. That's why the thickness is wider here, because this is P type, not P plus. This is N plus, right? Now let us start off. Now what we'll do is we'll analyze the thing in the scenario where the gate voltage goes from minus infinity to plus infinity. Okay, so we start off with very negative voltage. Okay, when we apply a negative voltage onto the gate, and the drain and source are connected like this, and of course the substrate is connected to ground. So what happens is that this PN junction and there is a PN junction over here, they are in a way reverse biased. There is no bias across them. They are certainly not forward biased. Okay, they are truly not reverse biased as well. They have zero potential difference across this, so there is a barrier potential and there won't be any current flowing between in this PN junction. Okay, now you apply a very negative voltage, so there will be negative charge over here will be there. Now if there is an insulator over here, so this will act like a capacitor. So what is the property of a capacitor? It will just store the opposite amount of charge on the other conducting plate. Okay, so therefore if I have negative charges here, there will be a bunch of positive charge over here. Okay, now the positive, so now what happens is that a P substrate anyway has the positive charge carriers. Okay, holes are the carriers. Okay, so now what happens is that these charge accumulate under the gate, and that's the reason we call it accumulation mode. Okay, it accumulates under the gate. Now what happens is that since there is a barrier potential over here, there is a depletion layer over here, there is a depletion layer over here, and there are positive charges over here, there cannot be any current flow between the drain and the source, because even if I apply a potential difference between the drain and source, there is a depletion layer and it is not going to allow the flow of current to happen. So in the accumulation mode, there cannot be any current flowing between the drain and source, and that is what is written here. So I have written here polysilicon gate is connected to negative voltage, resulting in some negative charge on the gate. So that's what I said, there is negative charge on the gate. The same amount of charge, but positive charge is mirrored at the other end of SiO2, that is in the P substrate. So the positive charge is mirrored over here. The negative voltage results in accumulation of holes or majority carriers of the substrate. So if it was a PMOS, then this is going to be, the substrate will be actually N substrate, or if I want to fabricate on the same substrate, this will be an N well, and therefore there will be negative charge over here in case of a P, and this will be P plus and this will be P plus. The similar scenario happens, but it will happen for a much positive gate voltage. Just the opposite, whatever is happening for a negative voltage here, in case of a very positive voltage, the same thing, accumulation of charge carriers will happen underneath the gate for a PMOS. Okay, so that's why I have made it generic. Negative voltage results in accumulation of holes or majority carriers of the substrate. Okay, if we apply some potential difference between drain and source, current is not going to flow. Okay, I have mentioned that there is a depletion layer over here, depletion layer over here. First, we have to overcome the barrier potential before any current can. We have to get rid of this thing so that any current can flow here. Note that PN junction and the source and drain are reverse bias or a zero potential difference. Depletion layer is there. Barrier potential prevents any flow of holes from P substrate to N plus source and drain region. Okay, so therefore there is no current flowing in the accumulation mode. Okay, so the accumulation mode, if there is no current flowing, what is the use of this? This mode is used to realize capacitors. Realize integrated capacitors. Okay, this is used to realize integrated capacitors. Also, you can use it as a discrete capacitor. If you buy that, you will see that it is capacitor is what? Capacity to store charge. So that's why it is called a capacitor. Okay, so now let's move on.
Sir, what do you mean by realize capacitors?
Realize a capacitor means if I want to have if I want to build a capacitor inside the chip, okay, I would try to operate the MOSFET in accumulation mode. Okay, so that is the way we would realize a capacitor, because capacitor I cannot show. I can how do I say? There are a lot of applications where I really so in introduction to electronics, have you studied something called a voltage doubler? Suppose I have
Yes.
So We have, let's say, a circuit like this, and so my clock waveform is going to be like this. Okay. So this is phi 1 and this is phi 2. How does the output voltage look like? What will be the output voltage in phi 2? So in phi 1, this capacitor C is charged to VDD. Then I disconnect these two plates of the capacitor. Now what is the charge stored across the capacitor? C times VDD, right? Then in phase 2, I connect this the bottom plate of the capacitor to VDD, supply voltage. So then what happens? I have to maintain the same charge across the capacitor. So that means V out will become 2 VDD, right? Does it make sense?
Yes, sir.
So now I can build something like this. So what we can do is I can connect a phase 2 here and have a load capacitor and define V out over here. V out is going to be V out will be equal to 2 VDD. Correct?
Yes, sir.
So eventually at t equal to infinity, it will finally reach a 2 VDD and maintain that unless I discharge the capacitor by load capacitor by connecting a resistor. So this is called a voltage doubler circuit. So what does it need? It needs a few things. It needs a capacitor and it needs switches. Now we'll see as we go along the thing that the MOSFET can be used as a switch and the MOSFET can also be used as a capacitor, and therefore it can be used to realize a voltage doubler. Okay?
Okay,
So,
sir. Okay, sir.
sir,
Yes. Yes.
sir, can you again explain the point about the depletion region being thick?
Oh, depletion region being thick. Okay. So if I have so think of it like this. When I was a kid, I think in kindergarten, our principal came to school, and in the final day, he asked all of us a quiz question. Which one is heavier? 1 kg of cotton or 1 kg of bricks? Both are equal, right? But which one takes more volume? The cotton, right? Cotton. So volume is dictated volume. So which side? This one has n plus. This region has more number of carriers. So the density of carriers is more. So in a smaller area, you can have, suppose, 5 coulombs of charge. To make the same 5 coulombs of charge, you would need a bigger number of carriers because the density is less. It is purely, that's why I gave this example of cotton and this brick. The density of the thing decides the volume. So that's depletion weight in n plus, and this thing is a function of the density of the carriers. Does it answer your question?
Yes, sir.
Okay. Now we start off with a very negative voltage, then we get to a 0 voltage. Once we apply a 0 voltage, what happens is that there is nothing, no charge on the top on the gate. So suddenly there won't be any charge on the P substrate, and these two are reverse bias PN junction. So this thing behaves like a back-to-back diode. So back-to-back reverse bias diode prevents any current flow from drain to source, even if we apply a potential difference between the drain and the source. Path from drain to source is very high resistance of the order of giga ohms, and the transistor is off. So, so that means this switch, if I use an NMOS over here, NMOS in this switch, I apply a gate voltage of 0, this is acting like an open switch. Okay, so this is how the MOSFET acts like an open switch if the gate voltage is 0 in case of an NMOS, and if in case of a PMOS, if the gate voltage is close to the supply voltage, then it acts like a open circuit or an open switch. Okay, now if we apply a small positive voltage, now we'll get into the formation of the depletion region. Depletion region again means we get rid of the carriers. Okay, keep in mind this was P substrate. Okay, substrate is sometimes abbreviated as SUB. Okay, so P substrate. So as soon as I apply a positive voltage here, positive voltage is going to repel the positive carriers over here on the P substrate. Holes are the carriers. Once you repel, what happens? You end up with the ions, and you have a anyway the depletion region was over here, you also extend it below the gate. Below the gate you have a depletion region, and there is another depletion region because of the PN junction, and no matter how much voltage you apply between the drain and source, there won't be any current flow because there are no mobile carriers over here. There is no mobile carriers over here, and therefore there won't be any current flow. Okay, so no charge carrier below the gate yet. So any potential difference between drain and source still does not result in flow of current. So typo here. Okay, in flow of current. Okay. So finally, we get to the, now if I apply, now we something called the creation of an inversion layer. So keep in mind what is the language here. Inversion, English word inversion means you are doing something, you are inverting something, and you are creating something called an inversion layer. That means inversion layer has to should be in a P substrate carrier. This is P sub, carriers are holes. By inversion, you are generating carriers which are electrons. So you have inverted the substrate. Okay, the mobile carriers in this substrate turn out to be the minority carriers, but truly they are not minor. There is something else. We'll get to that. What happens? Okay. So now when you apply a sufficiently large gate voltage, okay, and that sufficiently large is defined by something called a threshold voltage. Okay. So in this course, we'll be interchangeably using VTH as threshold voltage. Okay, VT also as threshold voltage. Okay, okay, so I'm taking the attendance right now. Okay, so download attendance list. I hope software is working correctly. Where does it download? I don't know. Okay, anyway, I'll figure out tomorrow. We'll get to know. VT is the threshold voltage. Sometimes we'll be using VT also to mean the same thing. Okay, so whenever in the problem, and keep in mind when VT has to be used as thermal voltage. In this course, we will tell you, okay, this is the thermal voltage. Okay. So please use the context and make sensible in the problem sometimes or anywhere. Use the context to understand the variables. So VT is thermal voltage in which is KT over Q, right? This is equal to KT over Q. K is Boltzmann's constant, T is temperature in Kelvin, okay? Q is electron charge, okay? KT over Q. So, we will be in a, because sometimes I write it as VT here because it is easier to write one letter rather than write this, or sometimes we write it like this. So we'll be interchangeably using this. So please understand from the context, okay? So now if the gate voltage exceeds a certain voltage, the threshold voltage, the electrons get attracted from the N plus source and drain. So the electron, these are majority of carriers which are electrons, they get attracted into the region below the gate on the surface of the substrate, thus creating a channel of mobile carriers. There is a channel of mobile carriers. Okay. The channel of mobile carriers are created on a p-type substrate. This induced layer of mobile carriers is also called inversion layer, as it is created by inverting the surface of the substrate. So the p-type substrate was inverted to have a negative ions, negative carriers, electrons here. Now in case of a PMOS, here it is an N-type substrate, so this will become holes over here. Okay, so that is what is going to happen. So that's why it is called an inversion layer. Now once the inversion layer is created, so we have a conducting plate. Okay, so this is acting like a conducting plate. Okay, and therefore if I apply a drain voltage, the amount there will be a current that will be flowing between the drain and source. Now who is controlling this this conducting plate? This gate voltage. That means this gate voltage decides how many carriers are going to be there. Okay, so for example, if I have a thin wire versus a thick wire, thin wire can carry less current, and as soon as it tries to carry more current, it burns out. Similarly, a thick wire can carry a huge amount of current. So now the thickness of this, or the amount of charge in this inversion layer, which is defined by this gate voltage, by how much is the gate open. Is it open a little bit, a lot, or a much more? So that depend on how much is this gate open. That controls how much carrier is there. Now when you apply a drain voltage greater than the source voltage, then what will happen is current is going to flow like this. In case of an NMOS, carriers will flow this way, current is going to flow in the opposite direction. Okay, current flow is opposite of the electrons. So that's why we say that drain will be greater than the source voltage. So the current will flow from the drain to source, or electrons from the source to drain. So as soon as you increase this, since there is a conducting region, so it will start carrying current, and the amount of current is defined by the amount of charge carriers that are over here, and which is further defined by the gate voltage that is applied on the thing. Okay, so now you have a controlling terminal, and this controlling terminal is going to decide the amount of current flowing between between the drain and source. And of course the controlling terminal, so therefore the current flowing between the drain and source is both, depending on the mode, we'll get into that, whether it is a constant current or whether it is going to be a current which is a function of the drain source voltage as well. So the current flowing between the drain and source can be a function of the gate voltage and can be a function of the drain voltage. So it is a function of two variables. Okay. The voltage at which the channel gets inverted is called a threshold voltage, VTH, and typical values of the threshold voltage varies from 0.2 volts to 0.7 volts. Okay. Now this, do not confuse threshold voltage with the VTH with the PN junction barrier voltage. Of course, barrier voltage is the 0.7 volt that you need, or 0.4 volts in case of germanium, right? Diodes. Okay, the polysilicon gate and channel region form a parallel plate capacitor with silicon dioxide as a dielectric. So as I said, this is one plate, and this becomes another conducting plate of the capacitor, and this is the insulator over here. Okay, so as the gate voltage is made bigger and bigger, more channel charge is created, that is conductivity between the drain and source increase. Okay, so basically I want you to remember these four pictures. Accumulation mode picture, remember it pictorially, equations will automatically fall in place also. Okay, then with zero gate voltage, how it looks like, the channel, then with inversion, how the channel looks like. So you have to remember these three pictures, and then there will be another picture as I make this sufficiently large. So now we'll analyze two scenarios. Okay, when VG is greater than VTH, means the inversion layer has been created, and the drain voltage is small. Now keep in mind in electrical engineering, we always have a reference terminal. We always fix a reference terminal with respect to which the voltage is always measured. Okay. So in this case, in case of an NMOS or in case of a PMOS, we always take the source terminal as the reference terminal. Okay. That means the provider of the carriers is typically considered as the reference terminal. So that means we are going to define VGS and then VDS. Okay. So when VDS is small, okay, we'll analyze two scenarios. When VDS is small and VDS is decently large, something else happens. Okay. Now when VDS is small, current flows due to electrons moving from source to drain. So that's a source of carriers. Okay, and carriers get drained at the drain. This current is called the drain current. Okay, so now I'll use certain notations for the drain current, and I would want you to, we'll be using those notations sometimes in the strict sense and sometimes in a on a contextual basis. So that we will make it clearer as we go along. Okay. Now the current is called the drain current ID. The magnitude of the current is a function of channel charge, which is a function of gate minus the threshold voltage. So this amount of this charge over here that is coming out is a function of the gate voltage. So we say that it is a function of VGS minus VTH. Okay, because when VGS is less than VTH, nothing happens. There is no charge carriers below the gate. Only when it exceeds, so by the magnitude with which it exceeds defines the amount of charge carriers below the gate. Okay. Thus, channel conductivity is proportional to the excess gate voltage, and this excess gate voltage VGS minus VTH is sometimes called the overdrive voltage VOV, sometimes called the effective voltage, and another name that is also commonly used is called the VDSAT. Again, three terms which mean the same thing, which is the excess voltage. Okay. Well, VDSAT, I would have introduced it later, but I'm giving you the three terminologies. So when VDS is very small, ID is proportional to VGS minus VTH. When VGS is the channel is enhanced to carry the current, and therefore it is called an enhancement type MOSFET. Okay. Now the next picture that I want you to remember is when VGS is greater than VTH, of course channel has formed, inversion has happened, but the drain voltage is decently large enough that the channel charge has this kind of a profile that the channel has pinched off at the drain end. Okay, so you can think of it a pipe through which water is flowing, and at some point you hold it tight, you pinch it off. Okay, so that is called the pinch off, the voltage at which, that means you have to apply a certain amount of force, and here in this case you have to apply a certain amount of voltage to pinch off the carriers. Okay, as VDS greater than, the voltage difference between the gate and the channel reduces from VGS to VGS minus VDS. Now think of it this way. So when gate voltage, so the amount of charge at this point is proportional to the gate. This is a conducting plate. So this voltage is VG, this voltage is VG. Similarly, at every point it is VG. But if I apply a voltage which is greater than, suppose I apply 1 volt here, then and this is 0 volts, okay, and this is 1 volt, okay, so it is 1 volt over here, 0 volt over here. So at this point it is going to be 0.1 volts, at this point it is going to be 0.2 volts, 0.5 volts, and here it is going to be 0.9 volts. Okay, it cannot, so if it is reducing like this, now the amount of charge below the gate, that is inversion that has been created, is a function of this gate voltage minus those instantaneous at each point, not instantaneous, at each location, okay, voltage. Now when this, and we know that when VG VDS equal to the threshold voltage, okay, there is no channel charge. So that means if VDS, the drain voltage approaches this VGS minus VTH, okay, VGS minus VTH, that means this voltage is overdrive voltage is 0 at this point, okay. And if that is 0, then there won't be any charge carrier right below the gate at that point. And that is when we say that the channel has been pinched off. Okay. So the channel there gets tapered, being deepest at the source and shallowest at the drain. If VGD equal to VTH, keep in mind, if this voltage and okay. So if this voltage minus the drain voltage equal to threshold voltage, okay, there will be barely any charge. As soon as it exceeds the threshold voltage, then the charge starts happening over here. So that's what is written like this. If VGD equal to threshold, then no channel is formed at the drain end, implying channel is pinched off. Pinch off happens at VDS equal to VGS minus threshold voltage. When VDS is greater than VGS minus VTH, then the VDS has little effect on the channel shape and the current remains constant at the value reached at VDS equal to VGS minus VTH. So what it means is that when I have pinched off the channel here, okay, at the drain end, after that if I keep increasing this voltage, the current flowing between the drain and source doesn't change, because after the pinch off has happened, the drain voltage is not going to impact the amount of charge that is underneath the gate that much. So the current therefore is going to stay constant, and whenever there is a constant current flowing between the any two terminals, the device is said to behave like a current source between those two terminals. Okay, and therefore this transistor MOSFET at that point after pinch off is called a voltage controlled current source. Okay, so that means it's a voltage controlled current source. So it behaves like, as I said, once the pinch off has happened, okay, then even if you change the drain voltage, then the amount of current flowing between drain and source is not going to change that much. It will change because of some other reason. In an ideal scenario, it is not going to change at all. And therefore, it behaves like a current source between drain and source. It behaves like a current source between drain and source. Okay, and but the amount of current flowing is a function of the amount of charge underneath the gate, and the charge underneath the gate is controlled by the gate voltage. So therefore, the amount of current flowing between drain and source is controlled by the gate voltage, and that's why the transistor behaves like a voltage controlled current source, or VCCS, voltage controlled current source. Okay, beyond pinch off, the drain current saturates. So you can think of it, when the drain voltage is very small, the channel is a straight line, is kind of rectangular. Okay, so as soon as you keep increasing the drain voltage, this instant difference at this point keeps on reducing, the overdrive keeps on reducing, so the channel profile keeps on moving upwards like this. And at some point at VDS equal to VGS minus VTH, the channel pinches off. There is no channel at the drain end, and then it behaves like a current source between a drain and source. So the channel profile as VDS is increased. So anyway, so there is a typo here. So does it make sense? Any questions on this?
So
Yes.
So if we increase the VDS further after VGS minus VTH, then the channel would pinch off further away from the drain, right?
Yeah, that I was getting to after some time. So then what happens is that the pinch off point keeps on moving, either it will keep moving closer and closer to the source. Okay, and that time we say that the electrical length of the channel is keeping on reducing. And that is called channel length modulation. Okay, so the drawn length is this distance between the source and drain, but after saturation, after pinch off, as soon as we keep increasing the drain voltage beyond pinch off point, then the channel, the pinch off point keeps moving closer and closer to the source, and therefore the electrical length of the channel keeps on reducing after pinch off. Does it make sense?
So yes, sir. But if there is no channel, how does the electrons then flow?
Yeah,
from?
so I'm getting to that right now. So now, as I said, if VDS is the voltage difference between the gate and substrate falls to VTH at some point L1. Okay, at this point, whatever is the voltage at this point, Vx, let's say, Vg minus Vx is equal to VTH. Okay, and here it is less than VTH and this region. Okay, and therefore there is certainly no channel. Now this is happening, this is there. Okay, so the channel is only up to this point. So now, does it mean transistor stops conducting? Okay, so what happens is that the thing is there is such a huge electric field between this point that the high electric field in the depletion region sucks the electron into the drain region. So there is something, I should not call it tunneling, but it is more like the high electric field pulls the electron and it suddenly goes out. Now imagine you have a pipe through which a high velocity liquid is coming and you pinch off at some point. Now the velocity, it cannot suddenly reduce to zero, right? The acceleration, that means you need a huge amount of energy, because velocity going to zero instantly is not possible. Then it will start radiating at that point. So now what happens is that, so the electron gets sucked into that drain at that point. So high electric field in the depletion region sucks the electron into the drain region. Okay. So modes of operation for VDS. VDS less than 0, we have accumulation. 0 to threshold voltage, we have depletion. Okay, and beyond, so this is the gate voltage. Sorry, this is the gate voltage with VDS equal to 0. As gate voltage exceeds threshold voltage, we have inversion. Okay, and in this region, it acts. The transistor acts like a resistor. Okay, and as soon as I change the drain voltage now, then it becomes a current source at some point. Okay, so with this, I think I'll stop today's lecture.